Polymerization occurs when monomers link together with other monomers. Two ways exist to create polymers of plastics. One way is through a chemical reaction called a condensation reaction. This is when two monomers, both usually with a hydrogen and an hydroxyl group attached, react with the help of a catalyst to create a polymer and release or lose a small byproduct monomer. The smaller monomer is usually water, alcohol, or an acid. The resulting polymer covalently bonds with other polymers to create a long polymer chain. One example is of nylon. 1,6-diaminohexane and adipic acid react and lose water to create polyamide or nylon. The other method is through addition reactions. This occurs with unsaturated monomers. The double or triple bond between the two carbon atoms in the unsaturated monomer react to form a new covalent bond with other nearby molecules. This creates a long addition polymer chain. For example, Teflon. Tetrafluoroethanes double bonds between the carbons are electron-rich, meaning that their bonds break easier than single bonds. Once one of the double bonds break, the lone electron from one of the carbon covalently bond with another tetrafluoroethane's lone carbon electron. Characteristics can influence the properties of polymers. Polymers can either be straight chains or branched chains. If polymer chains are branched, the dispersion forces occurring between the chains would not be as strong because the chains would not pack as close together. The properties of polymers with high branching are that they are soft, flexible, and frequently transparent. Side groups are a group of molecules that are attached to the main body or backbone chain of the polymer. They are a part of the repeating monomers in a polymer. Functional groups determine the chemical characteristic of a polymer. There are several functional groups, including alkyl groups, carboxylic acid groups, haloalkanes, alcohol groups, and esters. The arrangement of side groups is called tacticity, and there are three main ways that it can be arranged. The first way is when all the side groups are on one side, which is called an isotactic polymer. These are the most stable, as the arrangement allows for stronger dispersion forces to occur, since the side group patterns are the same. The second way is when the side groups are on alternating sides in a regular fashion. They are called syndiotactic polymers, and although they are weaker than isotactic polymers, the regularity of their structure allows for moderately strong bonds to occur between chains. The last way occurs when the side groups are randomly arranged on both sides of the polymer. They are called atactic polymers, and due to their random pattern, atactic polymers have the weakest bond of the three. As polymer chains lengthen, parts of the molecule can line up, whereas other parts tangle. The regions that are parallel are close together, and therefore stronger due to dispersion forces and dipole regions. Since they are arranged in parallel lines and are closer together, these regions are denser, opaque, and don't allow air, moisture, or chemicals to migrate through. From these strong bonds that form due to their proximity, the ordered regions are rigid and require more energy to move past each other. These are called crystalline regions. Amorphous regions, as they are tangled up parts of the chain, are weaker due to their chains being further apart, so the dispersion forces are also weaker. As they are spaced apart, these regions tend to be transparent and they allow air, moisture, and chemicals through. These regions are also less dense and flexible. As their dispersion and dipole forces are weaker, less energy is needed to make the chains move. Cross-linking occurs when parts of different polymer chains become covalently bonded. Sulfur atoms are used to create cross-links between polymer chains. Cross-links restrict the movement of the molecules. More cross-links make the polymer more brittle and rigid. The polymer chains cannot slip past each other when a force is applied. Once the polymers are formed, they cannot be remolded as they char rather than soften when heated. Occasional crosslinks allow the polymer to regain their original shape after being deformed. The small amount of crosslinking prevents the polymer chains from stretching too far. Instead, it pulls the polymer back to its original shape once the deforming force is removed. The elasticity of a material varies with the number of crosslinks between the polymer chains. Thermoplastic polymers have little cross-linking, and their dispersion forces are easily broken through the addition of heat. When this occurs, they become soft and pliable, but thermoplastic polymers are inelastic. Thermosetting polymers have extensive cross-linking, therefore they are brittle and when heated, they char. If enough heat is added, the polymer doesn't soften and instead the covalent bonds break. Elastomers are the medium between the two. They have occasional cross-linking, which prevents the chain from moving, but after being deformed, they return to their original shape. This is because the occasional crosslinks pull the chain back into their original shape. Here is an experiment that we did with milk and latex.